Just to clarify one point, let's do the calculation for this converter, right? So that's a pull converter, just 80% efficiency. Of course, can be done much higher. So this is one thing, 80% efficiency. Now, how much power does it process in percentage? Thing is, these are the two modules. So comparing this one to this one, this is 40% shaded, right? Because its short circuit current is 40% less. So that's the power that's going to be injected across this module. So that's 40% of one module, which is 10% of the entire installation, going through an 80% efficient converter, right? So calculation indicates about 2% losses. In practice, we had 3% losses. But you see, this is not a typical case in the sense that we only have just 2 modules. If we had 10 modules, we will be really close to 100% efficiency because we don't process the power actually. Because let's say, the best power processing is no power processing, okay? Okay, so we're starting part B. Don't worry, it's not much longer than part A. This is an example of ripple cancellation in a rectifier. Again, applying this concept of partial power processing. Just a simple example. So we already know that if possible, instead of having a converter which processes the entire power through it between the source and the load, maybe we can apply one of this arrangement here where partial power is being processed. Of course, this will be more advantageous as these voltages are closer to one another. Suppose maybe 10%, like in this example here with the transformer. And in this case, we have 4 options of doing this. So for the example I'm going to show, we use this arrangement, okay? Or actually this one. We increase the voltage relative to this source. So what's the idea? That's the rectifier system. And then we have the DC bulk, DC link capacitor, across which typically there is 350 volts or so, because this stage is typically a boost converter, and therefore the DC link capacitor has to withstand a little bit more than the maximum amplitude of the AC, right? For the boost converter to be controllable. But there are other applications. For instance, in this case, we did something for a communication system, and we did not use a boost converter. And then we had here a voltage of about 50 volts across this DC link capacitor. Now the thing is that this capacitor, in addition to the DC voltage, there is certain ripple at twice the line frequency. And there is nothing you can do in order to not have it by means of controlling. Because if you try to implement a tighter control here to avoid the ripple, then you disturb the input current. Then you'll produce harmonics. So you must allow for this ripple to develop across the capacitor. And then you have to get rid of this. So in most cases, what they do, they have another stage here that all the power goes through it, and it converts it to a different voltage level and also takes care of the ripple. In this case, with this system, we have a voltage here which is close enough to what the load needed. And then all we'd like to do is just, okay? And this is the implementation, not so important. Not so important. The thing is, this is V1, the input voltage, coming in here, and the output voltage, which adds on top of the voltage here of this DC link cap. That's just an implementation. It's not so important. So suppose this is the voltage that appears just schematically. It's not the right shape. The shape is sinusoidal at 100 Hertz. But schematically, suppose this is the voltage appearing across this capacitor. What I would like to do with this second unit here, just fill this gap so the load gets a nice DC voltage. Okay? Now, again, this is going to be a pool converter in terms of efficiency, because it has to, first of all, it's a low power converter. So that's one reason for low efficiency. Second, its output needs to vary a lot. So that's a second reason for the pool efficiency. Even though this converter has a pool efficiency, only a very small fraction of the entire power goes through it, and it is being processed by it. So the losses are, at the system level, are not that much. This is the input, of course, yeah, that's the switched mode rectifier. This is the voltage, this is the current, not so important. What's more important is what happens here. So you can see here, this is the capacitor voltage, or the input, and this is the voltage across the load. And if we put them one by the other, just to compare the ripple, we had the ripple very low, and maybe 40-something dB attenuated. This is the input ripple, this is the output ripple of the ripple cancellation unit. The variation of the voltage is in this full range of 1.2 up to 5.7. Obviously, the efficiency is very low, about 60%. The efficiency of the ripple canceller by itself. But at the system level, we reached some 92% efficiency, regardless of this 60%. Again, because of the low power that is being processed, and in the range of 160 to 200 watt load. So that's a second example of partial power processing. And this brings us to last part, which is a discrete step variac, or if you like, it's just an extension of the single phase thing that we had here. Just a simple extension, which somebody made eventually a lot of money. I just made some consultancy money out of it. So this is the thing. We have the line, the three-phase line. And suppose we'd like to reduce the voltage for some reason. We'll see a reason pretty soon. So that's a three-phase transformer. This is the primary, this is the secondary of this transformer. Secondary is connected constantly in series with the line, and with this polarity, it reduces the voltage towards the load. Okay? And the thing is, we can change the interconnection of the primary. We can feed it different ways. So the primary can be connected either in delta or in Y across here, but in addition, we can rotate the angles depending which primary phase we connect to each line. So altogether, it seems like a lot of options, and there are a lot of options, but they overlap. They overlap. So eventually, what we are able to do is generate three voltage reduction steps. So in this case, what they wanted is these voltages, and we could do this, is These are line voltages here at the load side. 260, 290, 360, and 400 volts, which is the situation where there is no voltage reduction. Maybe this one is the simplest to understand. How do we generate this one? We just apply a short on the primary of the transformer, so no voltage on the secondary. So the line equals the load, right? So there is no voltage reduction. That's the fourth step. And I'll explain a little bit how we generate the other voltages here. So one case is this one. This is the line, 400 volts, okay? And then on the secondary, primary was connected in delta as well. Primary was connected in delta as well. Have a look here. K1, K3, this. So for instance, this phase connects from line 1 to line 2, and so on. So suppose we choose a turns ratio of about 0.26. So the voltage drop across this guy here is 0.26 times the line voltage, right? And they are in the same phase. That's why we can draw them here, in the same phase. So this is the output. So this is the output. That's where we go towards the load. I'm sorry, that's a mistake. This should come from here, this line. How we reduce basic geometry, we can come up with this relation between the load side or the motor side. Eventually we feed a motor from this arrangement. So this is the relation where A is the turns ratio of the transformer, depending how we choose it, okay? But you can see already here that we can reduce the voltage. That's the maximal reduction, because these vectors here are the biggest ones because the primary is connected in delta as well. So these are the biggest ones, and also in phase, so that's the relation. The second step is attained, you might see here. Second step, K1, K4. All these points go here. And K4 creates what? A neutral point for the primary side of the transformer, right? So the primary is connected in Y. So the voltages that will appear across each of these windings are smaller, of course, and again rotated somewhat. So the situation is like this, and that's how we generate the second voltage level. Now they are no longer on the delta, but here. So they are smaller also. So in this case we generated 290 volts line to line. And this is the relation between input and output of this arrangement. And the fourth step is this case. So this is attained by K2, K3, which is again a Y connection of the input. If we go back here, K2, K3. So K2, neutral point, and these are connected at a certain rotation. So we get the smallest reduction, so the highest voltage, which is 358, which obeys this simple equation. Again, this is very simple to derive from simple geometry. And then, of course, there is the case when we short the primary. K2, K4, we apply a short circuit across the primary, and this short reflects on the secondary, and therefore there is no voltage reduction, and the input equals the output. So the motor voltage and the line input voltage are equal. And in general, well, we have this relation which relates the turns ratio of the transformer under different connections and to the voltage reduction. We have chosen here the point 26 because of what these guys wanted. What they wanted to do practically is kind of efficiency controller for machines, because there are many machines that are installed which are overrated. So, or looking at this another way, at many times, many machines are very lightly loaded. For instance, you know, lifts, they might be highly loaded, or depending on many things like this, moving stairs, escalators, etc. So if a machine is not loaded, the efficiency is very low and the power factor also drops. What we can do is reduce the voltage towards the machine. Of course, there are many more advanced ways to do this, but these ways are more expensive. They generate harmonics, they generate, you need high frequency switching, etc., etc., filtering and so on. This method is purely sinusoidal. You don't have any broken waveforms. Everything is sinusoidal. So this is the idea. That's the machine. Suppose that's the nominal operation point, but suppose it is loaded at a much lower point. So what we'd like to do is reduce the voltage. Just reduce the voltage. We can do this. We can do this because by reducing the voltage, we still can supply the torque because the machine is not loaded. Okay? So the curve now looks maybe like this, and the new operation point is here, which is closer to the nominal slip, which is better in terms of efficiency and in terms of power factor at the input. Okay? So they call this thing, that's a company, they call it efficiency controller, and they sell very well. They sell very well. That's basically about this product that they have. But the reason I mention it here is because it's again another example of partial power processing. And how about the issue of speed variation, right? If we reduce the voltage, people might think that we affect the rotation speed of the machine, but they need not worry because this is not an actual curve of a modern AC motor. They look rather like this. The curve in this region is very steep. So even if we reduce the voltage, we still operate pretty much at the rated speed. That's some experiment example showing that by reducing the voltage, we also improve the power factor. For example, we had here this controller applied to a fractional power machine. It's a small motor. Without the controller, well, it ran at 1450 RPM, consumed 365 watts and that many valves, and the cosinus fee is quite low. And then we ran it in with the same load, the same machine, with this efficiency controller. So by itself, it went to this value of the voltage, reduced the voltage to this point. Power factor was somewhat improved. Reactive power is reduced, and even active power is reduced. So about 50% saving of active power and 27% reduction of reactive power. But, well, we shouldn't get too happy, because remember, all these things are valid as long as the machine is loaded maybe at 20, 30, 40% of the nominal torque anyway. So, but anyway, there is such a product in the market. And the speed didn't change much. Even the voltage is reduced pretty much, right? From 400 to 285 volts. And the same thing, the same arrangement can be used also as for starting the machine. At the beginning, we apply a low voltage, and this is the current, this is the voltage. So we start with the low voltage. After a while, we increase the voltage, current goes up, and so on. So we can design it for start control, again, with no chopping, with no electronics. Everything is purely sinusoidal. So that's about it. Drawing the line between all these examples is that we should look for the possibility to process not the entire power, just part of the power that is really necessary to process, even if in some cases the efficiency is reduced for the processed power. At the system level, we still are in a better situation. For instance, examples you saw already. For instance, with this example, if we do appreciation of the power, so this is the input power, which equals the output power, and the power that cycles through this thing is really little power. For instance, at the maximum voltage here, it was 110 volts out of 400 volts, okay? But remember, when do we apply this? This is the highest voltage drop, highest voltage reading. We apply this when the machine is maybe loaded 20%, this 110 volts. So in practice, in the products that they sell, this transformer is rated at about 10 to 15% of the load power, which is nice. We have time for questions? Or?
Yeah.
What do you use for the switches? Just mechanical switches, or?
Yeah, well, here in most of the, actually in all the products they sell, they use mechanical switches, because this doesn't have to switch, you know, many times. It, like if it's an escalator, so most of the time nobody on the escalator, it just goes freely, and sometimes somebody comes, so once in a while. There are now some products that they are going to do for other applications with probably with IGBTs. We need more switches, more frequently switching. Yeah.
Do you suggest this method for larger motors? Because
they did it.
Transient times, torque oscillations, and
yeah, that's true. Yes, that's true. So for now, that's not for very large motors. For maybe up to 10 kilowatts or so. That's what they do.
Thank you very much.
Thank you.
We have a small present for you.
Wow.
And this is without your name at the moment, so you will give it back to me to receive it with the name
Oh,
on
great.
it.
Thank you.
Okay,
thank you so much.
Şöyle gelelim. Ha, şöyle yes.
We need to, yeah,
You are receiving it.
right, again.
Bekleyin.
Teşekkür ederim.
Ben teşekkür ederim.
Thank you. That's good.
I get it back.
All right.
Thank you.
Thank you.
Söyle adresini gönderiyoruz. Yazıp ismini.
Aslında burada halledelim onu.
Yazamayız burada hocam.
Hayır yazmayacaksın da ben sana kağıt vereceğim. Sen yazdıracaksın. Okay.